So, hello everyone again. This is lecture 3 part 3 of semiconductor electronics, materials, devices and simple circuits. In the last part of last lecture, we understood the concepts of n type semiconductor in extrinsic semiconductors only. Let us complete that discussion and then we can move on to the p type semiconductors. Okay. So, I am Samir Lavankar. Let us begin our discussion. Okay, so right now we are on the fourth topic, that is extrinsic semiconductors. Let us quickly complete this extrinsic semiconductors and then we can move on to the p-n junction. So, right now till the concept you already know, we are understood n type semiconductors. Similarly, we will understand p type semiconductors. You can understand that from the fifth point, that is p-n junction. Quite evident there will be some addition of p and n inside both the structures and there will be a junction being created, quite evident, n will be different, p will be different. If we join them, then those are called as p-n junctions. Just a quick explanation only, I will go on to p after the complete explanation of extrinsic only, just to explain to you what is happening, why the structure of this lectures are like this. Okay. Fine, then let us start extrinsic semiconductors. So, in the last lecture we were okay, so we have done till this point. Let us go on to the further discussion from this point now. Okay, so hence in an extrinsic semiconductor doped with pentavalent impurity, the electrons becomes the majority carriers and the hole becomes the minority carriers. New terminology, what are these majority carriers, what are these minority carriers? Majority carriers, just to explain to you, as the term says majority, so it are at a very higher value, and minority as in those are having a very lower value. What are the terms which we use to define it? Majority carriers are defined by so here majority carriers are basically Ne and minority carriers are Nh. When we will study p type semiconductors, in which majority carriers will be holes and minority carriers will be electrons. Why it would be happening, we will understand in subsequent slides, but for now we understood that electrons become majority carriers. Why? Because the conduction of electrons, that is value of Ne, are basically due to two types. One is intrinsic semiconduction, that is due to increase in the temperature there will be excitation of electrons from the covalent bonds to the out of the lattice structure, and because those are free electrons, they can move from one place to another place and hence there will be conduction. And second, due to the impurity being added, dopant impurity being added, there is an extra unbonded free electron present which can be used for the conduction of electricity. So, there are conduction being utilized by two parts and the holes are only due to the intrinsic semiconduction. Also, as the amount of conduction happening due to intrinsic semiconduction in the extrinsic semiconductor is very less, that is why the holes are also very less. Also, so all the complete summary of all the things which I just said is that the electrons are the majority carriers and the holes are the minority carriers. Okay. So, these semiconductors are therefore known as n type semiconductors. Okay. For n type semiconductors, we have Ne is greater than Nh. So, even if you do not remember anything, so you just need to remember, and but please remember everything. Just the one thing which you need to remember carefully is that for n type semiconductors we have Ne greater than Nh. Okay. Let us move on to the p type semiconductors now. Okay. So, as the name suggests, p type, everything which was present in n type, just reverse everything, you will get a p type semiconductor. What was happening in n type semiconductor? A pentavalent impurity was being used. What is being utilized in p type semiconductor? A trivalent impurity will be used. Okay, and everything, any majority carrier, every minority carrier will be just reversed. Okay, let us understand what is happening in p type semiconductor now. Okay, so this is obtained when the silicon or germanium is doped with a trivalent impurity like aluminium, boron, iridium, etc. Okay, so let us say we add a +3 element here. A dopant has one valence electron less than silicon or germanium, and therefore this atom can form covalent bonds with neighboring 3 silicon atoms only, but does not have any electron to offer to the 4th silicon atom. So, as you can see, as there is no electron here, we also understood this concept in the intrinsic semiconductor, that if there is no electron, we can understand that no electron is equal to hole being generated. Okay. So, what we can say, that there is either we can say there are no electrons, or we can say there is a generation or there is a hole present there. Okay. Fine. So, because as you can see that 3 bonds are intact, 3 electrons are intact, but because there is no 4th electron here, hence there is a hole being generated here. Okay. What happened to the generation of hole now? Okay. So, the bond between the fourth neighbor and the trivalent atom has a vacancy or hole as shown in the figure. So, this is the hole being explained. Since the neighboring silicon atom in the lattice wants an electron in place of a hole, an electron in the outer orbit of an atom in the neighborhood may jump to fill its vacancy, leaving a vacancy or hole at its own side. So, what is being explained in this fourth point here? Let us say as a hole is being generated, it will try to acquire or to make its covalent bond. So, what it will say? It will take this electron from this portion, or let us say it will take this electron from this portion. So, there will be electron jumping happening and electron will be residing at this portion now, and there will be a hole being generated in this portion. Only this thing has been explained in this fourth point, and this cycle can go on. Then there is a hole generated here. Let us say this electron can move to this portion and there will be a hole generated here also. There will be electron being imparted at this portion then, and this cycle can go on, or these steps can go on. Thus, the hole is available for conduction. Okay. So, here what we can say that the hole is available for conduction in present here only. Till now we have not gone into intrinsic semiconduction till now for this p type. Till now we can understand that the hole is being used for the conduction of electricity in p type semiconductor. Okay. Note that the trivalent foreign atom becomes effectively negatively charged when it shares fourth electron with the neighboring silicon atom. Quite evident. Is it having plus 3 now? So, note the trivalent foreign atom becomes effectively negatively, quite evident because the stable state for the trivalent atom is plus 3 only. If you try to increase an electron for its conduction, then there will be negative charge, quite evident. If an electron is being added, then negative charge is being added into the trivalent atom. Note that the trivalent foreign atom becomes effectively negatively charged when it shares fourth electron with the neighboring silicon atom. Therefore, the dopant atom of the p type material can be treated as a core of one negative charge along with its associated hole as shown in the figure. Okay. So, what we can say is, we can say that this is some core, this is some core which is having a negative charge and also a hole. Okay. It is obvious that one acceptor atom gives one hole. One acceptor atom as in, okay, one thing more, one terminology again more. So, when we were understanding the n type semiconductor, it was, if you remember correctly, it was being called as your donor impurity or donor semiconductor. Why? Because it is having an electron, so it is being donating, it is donating one electron, right. What is a p type semiconductor? It is accepting one electron, hence acceptor semiconductor, and hence the name is here. So, just another terminology, another definition, n type semiconductors are also called as donor semiconductors and p type semiconductors are also called as acceptor semiconductors. Okay. Move on, let us move on. So, these holes are in addition to the intrinsically generated holes, while the source of conduction electrons is only intrinsic generation. Okay. These holes are in addition to the intrinsic generated holes, while the source of conduction electrons is only intrinsic generation. Okay. So, what does it try to say is here, till now we have not understood the concept of intrinsic generation, in which we say that the holes are being generated due to the increase in temperature. But if we say as a whole, the p type semiconductor, in p type semiconductor the conduction or the generation of holes happen first due to the trivalent impurity being happening, and second due to the increase in the temperature also. Thus, for such a material, the holes are the majority carriers and electrons are the minority carriers, just the reverse. Why there is a reverse? Because the n type semiconductor were the donor semiconductors and the holes are your acceptor semiconductors. Okay, fine. Therefore, extrinsic semiconductors doped with trivalent impurity are called as p type semiconductors. So, just to remember, as the name suggests, n type. So, n can be said as negative. Negative refers you to the negative electron, as electrons are negative. So, those are called as your donor impurities, and p type, as we can say, p is positive. Positive is basically holes, we can refer positive to holes, and hence these are your in which holes are majority carriers. In n type, electrons are your majority carriers. Okay. So, for p type semiconductors, the recombination process will reduce the number Ni of intrinsically generated electrons to any. So, here what we can say is, in the previous discussion what we said was there were only 4 holes and there were 16 electrons. This time what will happen is, there are, let us say, 16 holes and only 4 electrons. So, what will happen is, there will be some there can be a time in which all the electrons are inside these holes only, and then the conduction will happen due to the movement of these holes. So, some electron from one portion can go to another hole, and hence because of this movement we can say that there is a movement of electrons, or we can say there is a movement of holes. Due to this movement the conduction happens in p type semiconductor. Okay. So, for p type semiconductor the recombination process will reduce the number of Ni of intrinsically generated electrons to any. Okay. For we have for p type semiconductors NH is greater than Ne. Okay. So, for if N type was Ne greater than NH, and NH is very greater than Ne. Note that the crystal maintains an overall charge neutrality, as the charge of additional charge carriers is just equal and opposite to that of ionized core in the lattice. Okay. So, what does it try to say is that the complete crystal maintains an overall neutrality. So, there will not be a complete plus, let us say 10 to the power 6 charge or 10 to the power 4 charge, depending upon the amount of lattice structure happening in, let us say N type semiconductor, or let us say positive charge due to the p type semiconductor. The complete substance will be happening having a overall charge neutrality, as the charge of additional charge carriers is just equal and opposite to that of ionized cores in the lattice. Okay, fine. More discussion on p type semiconductors here. So, in extrinsic semiconductors, because of the abundance of majority current carriers, the minority carriers produced thermally have more chance of meeting majority carriers and thus getting destroyed. So, just to explain you, what does it try to say? Let us say we take an example for your N type semiconductor. In N type semiconductor, the electrons were the majority charge carriers, the holes were the minority charge carriers. Let us say there are 4 holes and there are 16 electrons. There may be a time in which all these 4 holes will be utilized by the 16 electrons. So, in one way what we can say that there are 12 electrons and 0 holes. Let us move on to the example for your p type semiconductor. Let us say what happens in p type semiconductor, the holes are the majority carriers and the electrons are the minority carriers. So, let us say there are 16 holes and 4 electrons. There may be a time in which we can say that the 4 holes are being utilized by the 4 electrons. So, in one way what we can say there are 0 electrons and 12 holes remaining. So, in another, so it is just a way of saying that the minority carriers are being destroyed due to this majority carriers. Okay. So, in extrinsic semiconductors, because of the abundance of majority current carriers, the minority carriers produced thermally have more chance of meeting majority carriers and thus getting destroyed. Okay. Hence, the dopant, by adding a large number of current carriers of one type, which becomes the majority carriers, indirectly helps to reduce the intrinsic concentration of minority carriers. So, this is just a way of saying that when we try to add the dopant tries to reduce the intrinsic concentration of minority carriers. Okay. The semiconductor's energy band structure is affected by doping. Okay. In the case of extrinsic semiconductors, additional energy states due to donor impurities ED and acceptor impurities EA also exist. Okay. So, the complete concept which we understood in your band theory of solids, in which there was an energy gap EG existing, right. Due to the addition of doping, there is a further distortion, or there is a further modification happening in this band theory of solids. What is this modification is being explained in this line. Okay. So, what does it say? That when we try to work, or let us say we try to add a dopant into a semiconductor, the additional energy states due to donor impurities ED and acceptor impurities EA also exist. So, as you can see, there is a ED existing here. Similarly, there would have been a EA existing in your another type of semiconductor. Okay. So, this is only the thing, band structure modification, the band structure being added up. Okay. So, in the energy band diagram of N type semiconductor, I guess this is for N type semiconductor only, the donor energy level ED is slightly below the bottom EC of the conduction band, as you can see, and electrons from this level move into the conduction band with very small supply of energy. So, what does it say is, so please be very careful. It just says that in one way, in virtual sense, what we can understand is the valence band is surprising of this complete area now. So, basically the amount of energy required for the electrons will be only 0.01 electron volts. So, that is the thing, or that is the virtual explanation of what this ED line tries to explain to you. Okay, fine. So, this thing is explained. So, basically there will be the electrons from this level move into the conduction band with very small supply of energy. Okay, so we can say that in one way or the other, the valence band is being increased to the maximum value of ED here, so that the energy gap now remaining is only 0.01 electron volts. at room temperature, most of the donor atoms gets ionized, but a very few, that is 10 to the minus 12 atoms of silicon gets ionized. Okay. So, donor atom gets ionized very quickly, but only few atoms of silicon gets ionized. So, the conduction band will have most electrons coming from donor impurity. Please remember this is very important line. Majority of the conduction electrons, majority of the electrons in the conduction band are basically due to the impurity. Why? Because at room temperature the ionization energy, or let us say the amount of ionization happening for the donor atom is very higher as compared to silicon atom. Finally, what we require as a person is that there should be a conduction of electricity. If it happens from the donor or it happens intrinsically is not our case, is not our thoughtfulness also. For finally, we need a conduction, we need electricity, right. So, but if we try to understand what is happening here, actually is the amount of electrons which are being present here, majority of them are only and only due to the donor impurity. So, the conduction band will have the most electrons coming from the donor impurities as shown in the figure. Okay. I guess similar situation will be for your this p-type semiconductor, only this time the EA value will be here, right. So, this time similarly for p-type semiconductor, the acceptor energy level EA is slightly above the top EV of the valence band as shown in the figure. So, virtually what we can say is in some way or the other the conduction band has come down and this is your virtual conduction band now. Okay. So, with very small supply of energy, an electron from the valence band can jump to the level EA. Quite evident because this is very small value, only approximately 0.01 to 0.05 electron volts, and ionize the acceptor negatively. Alternatively, we can say that with a very small supply of energy, the hole from level EA sinks down into the valence band. Okay. So, one way or the other we can say that the electron has moved apart from one place below band to above band, or we can say that the hole has moved from the above band to the below band. Just to explain again so that no confusion happens, either we can say that the electrons are moved from the below band to the above band, or we can say that the holes are being moved from the above band to the below band. Okay. At room temperature, most of the acceptor atoms gets ionized, leaving holes in the valence band. Okay. So, just the difference, just the opposite parts are happening here. So, most of the acceptor atoms gets ionized, leaving holes in the valence band here. So, as you can see, holes are leaving in the valence band. Thus, at room temperature, the density of holes in the valence band is predominantly due to the impurity in the extrinsic semiconductor. Okay. So, majority carrier concentration takes charge here. The electrons and the hole now this please be very careful. The electrons and hole concentration in a semiconductor in thermal equilibrium is given by this. So, either if we have the intrinsic concentration and let us say we have the concentration of holes, we can find the intrinsic concentration of conduction electrons also. We can find the value, let us say we have the value of Ni, we have the value of Nh, we can find the value of Ne. Okay. Though the above description is grossly approximate and hypothetical, it helps in understanding the difference between metals, insulators and semiconductors, extrinsic and intrinsic in a simple manner. Okay. So, finally, the final conclusion is till now, please be very careful now. So, okay. So, in intrinsic semiconductors we understood that Ne is equal to Nh is equal to Ni. Ni is the intrinsic concentration of the atom. Ne is the number of conduction electrons, Nh is the number of holes. In extrinsic semiconductor we understood two types, one is pentavalent and another is trivalent. In pentavalent we understood that Ne was greater than Nh. In p type we understood that Nh was greater than Ne. Finally, just to what we can say, just to calibrate or just to find a relationship between the intrinsic and the extrinsic, we understood a new formula, that is Ne multiplied by N, the product of Ne and Nh is equal to Ni square. Okay. So, please remember this may be used in some of the examples which we understood in transistors, diodes, etc. Okay. So, let me stop the discussion here only. In the next part we can go with the further discussion of extrinsic semiconductors, and then we can move on to the next topic, that is your PN junction. Okay. Okay. So, the course progress till now, we are already completed with the introduction part, the classification of metals, conductors and semiconductors, intrinsic concentration, intrinsic semiconductors, and right now we are on the fourth topic, that is extrinsic semiconductors. I guess only 10 minutes will be required for extrinsic semiconductors, and then we can move on to the PN junction. Okay. So, that is the course progress till now. We will keep on understanding every topic and then we can finally complete the semiconductor devices. Okay. So, for this lecture, thank you so much.